So during my introduction, I pulled out various semiconductor components and I showed you the kinds of things that you're using in the lab that are already made out of semiconducting materials. One of those was an LDR, so a light-dependent resistor, or a photocell, they're sometimes known as. And hopefully you can understand now how these work, because actually, if you look at the band gap diagram, you've got a valence band that's full, you've got a conduction band that's empty, and you've got a band gap. Now, if light falls onto the material that is of a large enough energy, then electrons will go from the valence band to the conduction band. So instead of thermal emission, you've got the absorption of light energy. And hopefully you know that the energy is also equal to HF. And you've got so it's frequency dependent. So that would be the case if you have an intrinsic semiconductor. But of course, if you have something that's doped, then actually you have impurity levels in the band gap, and the energy that you need in order to get electrons from that state into the conduction band is much, much less than it is for them to go over the band gap. So actually this takes very little energy. So you can see here that in a circuit, if light falls onto a photocell, its resistance will change depending on the amount of light. So as you get more and more light, you get more and more electrons in your conduction band, so more current will flow. And these are the kinds of things that are used in automatic doors and motion sensors, solar panels, things like that. So there are all sorts of applications for these kinds of semiconductors. So you know that E equals HF, so you know that the energy is directly proportional to the frequency of the light. So you can do all sorts of calculations to work out what frequency of light is necessary in order to get conduction in these types of materials. You also need to know how to convert between electron volts and joules, because in the industry we tend to talk about the energy given in electron volts, but all your calculations need to be done in joules, and then you convert back to electron volts. So just be aware of that as well. It's this exact absorption of light energy that gives diamonds their color, because I said earlier that carbon is also a semiconducting material. And if you look at diamonds, well, the reason why they look clear is because light is traveling all the way through the diamond, from the light source to my eyes, so it looks transparent. But when you have impurities in the diamond, so the impurities are exactly the same as the way that dopants act, you actually get absorption of light at different frequencies depending on what impurities you have in the system, and that's why diamonds appear different colors. And where you find them, it determines what color they are if they're naturally found, because they will have absorbed impurities from their surrounding environment. But we also can manufacture man-made diamonds these days, and we can manufacture them to different colors by adding different dopants. In the same way that diamonds absorb the light that is coming through them, because they're a semiconducting material with a band gap, or with these donor and acceptor levels. Is this the same way that LEDs also give out light, but it's the reverse process? So in an LED, you get light given off as electrons that are already excited into the conduction band drop down into the valence band, and they give off light at very specific frequencies, and that determines what color your LED is. So it's actually the material, the semiconducting material inside your LED, that determines the color and the frequency of the light that's given off. I know that in the lab you might have thought that the LEDs, they're in a little plastic case that is a certain color, and you might have thought, oh well, maybe it's just a white light inside and we just color them by putting different plastic caps on. But no, the LEDs are actually colored, their color is dependent on the material that they're made out of. And the only reason we have them in the plastic casing is because otherwise, the problem is, if sometimes you can order them, they're all in clear casing, and if you get them mixed up, you can't tell which color is which until you plug them in. So that's exactly how LEDs work. And in fact, hopefully now you should also work out what was happening in that video that I added from YouTube in my introduction